Okay, good day. This is dual enrollment, free calculus. I am Mr. McCauley. This is lesson 1, and it is a lesson that will cover functions, different quotients, increasing, decreasing, and extrema. It is covering a number of topics that are in a few sections of the book. Remember, this first portion of pre-calculus is a review from Algebra 2, so we do have to move quickly as there is a fairly shortened time component to this course. So let's get right to it. So today we're going to review function notation. We are going to talk about use of function notation to simplify the difference quotient. And we're going to determine open intervals on which a function is increasing, decreasing, or constant. And then we're going to use technology to find relative maximums and or minimums. And then we're going to determine if a function is even or odd. So right off the top, we'll hit that first one. A function notation is a method of describing functions in which we normally call the input a value x and the output a function f of x. And that's what these two symbols represent respectively. Function notation, f of x is equal to 3x plus 1. This is a specific function. And we could say for instance, if I get the proper tool, we could say find f of 4. Now that f of 4 means that we would take 4, plug it in for x, so we would have 3 times 4 plus 5. And so 3 times 4 is 12. 12 plus 5 is 17. So f of 4 in this particular instance is 17. Now, the difference quotient is, I suppose I'll start right this. The difference quotient is a ratio composed of functions, and it is modeled after the slope equation. All right, so it is also a basis of a significant definition in calculus. If you get to calculus, you will see this particular thing again. So let's talk an example here. It says find the difference quotient and simplify the answer for the given function f of x equals 2x minus 1. Okay, so if we remember the difference quotient from the last one, it was f of x plus h minus f of x all over h. Now, just like in this last example, we plugged in a numerical value 4 for the function, we can also plug in an expression for that function. So just like I plugged in a 4 in for x in the last one, I'm going to plug in this expression x plus h. So f is defined as 2 times something we don't know minus 1. So when I do that, just this portion right here, it becomes 2, and we are replacing x with x plus h. So x plus h, that goes in for the x. We still need the minus 1. So now we have just done this f of x plus h. Then it asks us to subtract f of x. Okay, so f of x is this thing, but we need to remember that we are subtracting the whole thing. And so that I remember that, I'm going to put it in parentheses. So f of x was defined as 2x minus 1, and we'll leave that, and it's all over h. Now that is finding the difference quotient. Second thing it asks us to do is to simplify the answer for the given function. Okay, so we're going to simplify this. We have a couple things that we can do. First thing that we're going to do is we're going to distribute the 2 to both functions both terms inside this parenthesis here, and then we're going to distribute the negative sign to both terms inside this second set of parentheses. So let's do that. I'll have 2x plus 2h minus 1, and then distributing the negatives, I'll have negative 2x, and then remember negative of a negative is positive all over h. And so then we want to collect our like terms. So I've got a positive 2x right here. I've got a negative 2x right there. Those two cancel out. I've got a negative 1 right there. It cancels out with positive 1 right there. And all we are left with is 2h over h. And if you remember reducing our rational expressions from Algebra 2 last year, we can cancel out those h's, and we will be left with, as our final answer, just 2. So the simplified difference quotient of the function 2x minus 1 is just 2. All right, let's talk about increasing, decreasing, and constant functions. All right, so a function over a given interval, f, is increasing if for any x1 or x2 that is in the interval a to b, then the function value of that first point will be less than the function value of the second point. Now, let's talk about what that looks like in a real example. So let's say I talk about from here A to here B. All right. Let's say I have this function that comes down like this, and then goes up, and then doesn't look like it's all the way to B. I want to make sure that I'm not missing any. Uh-oh. Ooh, didn't want that. There we go. Make sure that I'm going all the way up at B, and then we can start coming back down. Okay. All right, so here's my function f, and we want to talk about, I can say that this function here is increasing if I pick any two x values. So I want to pick a point right here, x1, and here x2. So again, we pick these arbitrarily. We're saying that from a to b, this function is increasing, and I could pick any 2 points, x1 and x2. And so if x1 is less than x2, and clearly that is, if we talk about our number line from going from left to right, then f of x1 will be less than f of x2. And we can see that in this particular diagram, because if I come up from x1 to here and come over to there, that's my f of x1, and it's just a coincidence that it crossed the y-axis here. My poor drawing skills. And this point over here is f of x2, and so clearly f of x2 is less than f of x1, and so that's how we see a function is increasing. When a function is decreasing, if I pick any x1 and x2 that are elements of a to b, so any x1 and x2 where x1 is less than x2, then the x1 value will be greater than f of x2. And so we can go back down to, maybe we can go back down to it. There it is. We go back down to the slide right here that I just did. And let's erase some of this stuff here. We don't need to erase all of it. We like to keep everything. But if our function is decreasing from a to b, and it doesn't have to stop at a to b, we're just making any open interval, and it could go up or down. But clearly, if I say, and the only thing I have to erase here is this, and I suppose we'll change it to decreasing. If x1 is less than x2, and again, x1 is x2, and I can pick any x1 or x2 that I want, then if the function is decreasing over a to b, whoa, I didn't mean it to do that, then f of x1 will be greater than f of x2, and we can clearly see that here as well. So this point right here on the y-axis is my f of x1, and it is clearly less than the value for f of x2. Now finally, if we want to talk about constant functions, for constant functions it's fairly simple. Any x1, x2 that's an element of a to b, then f of x1 and f of x2 are equal. I can show that, but it's fairly straightforward. Constant function is going to be one in which you have a horizontal line. And so horizontal line would look like this. Here's my constant function, and in this case, this point right here has f of x1 being equal to f of x2, and that's for a constant function. All right. Okay, let's talk about the next term. Wondering why it's giving me a hard way to go about switching. Okay, extrema, relative extrema. A function value f of a is called a relative minimum of the function of f when there exists an interval x1 to x2, and the last one it was a to b, but this is directly from the book, so I'm copying there, contains some x value a such that for any value, any x that you pick between those two, f of a is always going to be lower than f of x. So let's talk about an example of that. So if I want to talk about a relative minimum, let's talk about something that looks like this. Let's give an x1 and an x2. All right. Here is my point that I'm going to call a f of a. And this is what I'm calling as my relative minimum, a f of a. That's my relative minimum. Any other point that I pick between x1 and x2, and that should not look like as if it were squared, so let me do a better job there, x2. Any other point that I pick here, if I pick this one at random and I call it x, then f of x is always going to be bigger than f of a. So f of x has to be bigger than f of a, although I think I wrote it opposite in the notes portion. All right. And so going back, a function value has a relative maximum, and it looks like, oh, there it is, if x is always bigger or smaller than f of a. So if I want to do a maximum, it's going to be something similar to that. We want to call this a relative max. We want to change our diagram just a little bit here, and we want to say that if this is a relative maximum, then f of x is always going to be smaller than f of a. So if I draw in, not there, come on. Yeah. If I draw in a point here, and I'm going to move a so that I can get it where I want it to be, maybe. I'll grab this a and move it so that it's where the maximum is, right here. That's my maximum. There's my f of a. We want it to be a relative maximum. Then any point in between these two open intervals, x1 to x2, if I pick any point, and this point right here will be x, f of x, then this point, f of x, must always be smaller than f of a, which is this point right here, a, f of a. There we go. All right, so there's my visual representation for a relative maximum. All right, so using a graphing calculator, let's talk about, I have an example in my graphing calculator and go to it in a second, but let's talk about what we're doing here. And so a question will be phrased like this: use the given function to determine determine the open intervals are, on which the function is decreasing or increasing and any relative extrema. So we got two things here. We're going to have intervals. So part A, intervals. Oops, I wanted to circle that. And part B, we're going to have extrema. All right. So I have an example here. And my equation is going to be negative x squared minus 5x. And hopefully you guys will notice that, or at least recall from last year, this is going to end up being a parabola that opens down. So when I hit the graph button, we see a parabola that opens down. And for a while, this function is increasing, and then it starts decreasing. We can see that. And so the extrema here is going to be the point where it changes from increasing to decreasing. And so we're going to find that. So once again, we're using the trace key, but we never use the trace key alone. That's never going to be accurate enough for us. And we're always going to use the second function. So I'm going to go second, I'm going to go trace. I'm going to bring up my my maximum in this case function. So we're going to hit 4. And so I want to make my maximum and minimum. I'm going to go a little bit to the left of where I think the maximum is for this particular one. So I'm going to a little bit to the left, enter. And I'm going to go a little bit to the right of where I think that function is. So I'm kind of, if you look back to here, relative extrema, what we're doing here is we're kind of setting up this bound, these two bounds of where we're looking for the biggest value in between those two arbitrary points. So I hit, that says guess, and just to be clear, the guess means it wants you to put it as close to the top as possible, but on something as small as this, it doesn't really change it. And so here we see that it says negative 2.499999. We're going to round that to negative 2.5, and the y value at 6.25. So we're actually answering the extrema question first. We have a relative, and in this case it's absolute max. And the reason it's absolute, just so you know, there's nothing higher. This thing never goes back up. It's nothing higher than that. But if we had a function, and I'm opening a can of worms that I didn't really want to get to, but we'll do it real quick. If I have a function like this, this function here has a relative maximum right there, but it doesn't have an absolute maximum because it goes up forever. And it has a relative minimum here. Has a relative maximum here because relative to a arbitrary distance away from that is the highest point, but it never has an absolute maximum. This is a relative minimum, but it never has an absolute minimum because it never goes any, or it keeps going down forever. But in this particular instance, it goes down to the left and down to the right, so there's nothing higher than the point that we've come up with. Okay, that's a quick explanation. So in this case, we have a relative absolute maximum, and I said it was negative 2.5 comma 6.25. All right, so this is the point where it changes from increasing to decreasing. All right, and so the intervals, we're going to say this function is increasing on, well, the open interval, it starts from negative infinity and goes to negative 2.5. And so look at the picture here. So from negative infinity, and can make this a little bigger. Oh, look at that. That's pretty. All right, so from negative infinity over here off the window all the way till we get up to this point at negative 2.5, this function is going to be increasing. And then from that point until we go off the screen and over to infinity, it's going to be decreasing. So from negative infinity, positive negative to negative 2.5, this function is going up. And again, this is an interval of x values. All right, we're just talking about, just real quick, we're just talking about this area right here. All right. And then it is decreasing on negative 2.5. Uh-oh, I didn't want that. Let's cut that. There we go. To positive infinity. All right, and again, this is also an interval of x values. It's increasing or decreasing. Okay, Finally, even and odd function. A function f is even when for each value in the domain of f. If you were to plug in a negative x value, you would get the original function back out. And a function is odd when for each x value in the domain of f, f of negative x is equal to negative f of x. And so just as a little note, all right, even and odd functions are actually pretty rare. All right, most functions are neither. Okay, so let's talk about two elementary examples. Let's talk about f of x equaling to x squared. This is going to be an example of an even function. This is the original. If I plug in negative x, so I'm going to go f of negative x, all right, I get the quantity negative x squared, and we know that negative x squared would be negative x times negative x. That's going to give me just x squared, and this is the original function. Since I plugged in negative x and I got the original function back out, this is an even function. All right. If I took f of x equals x to the third, this is my original function. All right. If I plug in negative x, I'll get f of negative x. That would be the same as negative x to the third, which we could write as negative x times negative x times negative x. Well, x times x times x is x to the third, but negative times a negative times a negative is still negative. Excuse me. So this function, when I plug in f of negative x, I get negative, let's go back here. I get negative f of x out. It's just like I took this function and I made it negative. If I say take f of x equaling to x to the third, and I say multiply that by -1, and I distribute to every term, I get negative f of x equals negative x to the third. All right, so this function is odd. And finally, just a simple neither function. If I say f of x is equal to, let's say, 2x minus 1, and I say we're going to plug in f of x, f of negative x, we'll get 2 times negative x minus 1, which gives me negative 2x minus 1. Now that's not the original function. The original function was 2x minus 1. And if I say -1 times f of x minus or equal to 2x minus 1, I make the f of x negative. It's negative f of, oops, let's do a better job. My pad is acting funky today. F of negative x. And then I have to distribute a negative to both of those two terms as well. So negative 2x, and then negative and negative becomes plus 1. So this function, this is neither f of x, nor is it f of negative x. So this particular function is a neither function. All right, those are some quick examples. And so we're finished with the day, so we will finish up with our Star Wars fun fact of the day. Most everyone knows that the creatures in that picture are called Ewoks. But that word is never spoken in any Star Wars movie. So that's my fabulous fun fact of the day. Hope you have a good day. I'll see you next time. Goodbye.